Okay. The next is your from equation 3 that H P g is equal to alpha dash upon P g plus beta dash plus gamma dash P g. This is say equation 1, right. So, that 3 measurement data actually given to you, right. So, the 3 measurement data gives 3 points on the curve and hence we can solve 3 unknown coefficient alpha dash, beta dash and gamma dash, right. 25% of Pg is that is equivalent to that it is 50 megawatt rating. So, it is 12.5 megawatt and correspondingly HPG is given data given that is your 10 mega kilocalorie per megawatt hour. This is given because this is the data given here, 25%, 40% and 100% it is given here, right. Similarly, 40% of Pg that is 20 megawatt, right, 40.4 into 50. So, that is HPG corresponding to that 8.6 mega kilocalorie per megawatt hour and 100% of Pg means 150 megawatt. So, that is HPG is equal to 8 mega kilocalorie per megawatt hour. So, in that equation 3 you put this value, right, Pg value and H value. So, this is alpha dash by 12.5 I mean this equation. In this equation you substitute H value and Pg values for different rating, right, different power generation rather, right. So, it is alpha dash upon 12.5 plus beta dash plus 12.5 gamma dash equal to 10, this is equation 2, alpha dash by 20 plus beta dash plus 20 gamma dash that is 86, that is 3, and this one alpha dash by 50 plus beta dash plus 50 gamma dash is equal to 8, right. So, these 3 equation linear equations. So, you can solve these linear equations your what you call using your calculator, right. If you solve this then alpha dash, beta dash, gamma dash value will get, right. That means, you solving equation 2, 3 and 4 the 3 linear equation you will get alpha dash is equal to 55.56, right, beta dash is equal to 5.11 and gamma dash is equal to 0.0355. Therefore, cost of fuel K is taken as a 4, right. Therefore, A is equal to we have seen K alpha dash that is multiply this one by 4. So, 4 into 55.56. So, 222.24. Similarly, B is equal to K beta dash that is 4 into 5.11 that is 20.44, right, and D is equal to K gamma dash. So, 4 into 0.0355 is equal to 0.142. So, fuel cost function therefore, is given by that you substitute in that expression of A plus B P g plus your what you call D P g square. So, it is 222.24 plus 20.44 P g plus 0.142 P g square. This is that function of C P g you have obtained, right. Now, you have to find out that what is C P g at your 25% rating. At 25% rating means 50 megawatt it is generator. So, it is P g is equal to 12.5 megawatt. Therefore, C P g will be this P g value you substitute here, right. So, you will get C P g is equal to rupees say 500 per hour, right. Just you will give a this will give you a feeling that how you can go for solving such things, right. Similarly, at 40% rating again P g 20 megawatt put in that expression, right, you will get it is rupees 688 per hour, and at 100% rating when P g is equal to 50 megawatt P g is equal to 50 you will get rupees 1599 per hour, this is C P g, right. Now, this incremental cost when you will take you have to take the derivative of C with respect to P g, right, with respect to P g, that means incremental cost C P g will be 222.4 plus 20.44 P g plus 0.142 P g square, this we have obtained. Now, take the derivative d C by d P g, d C d P g is equal to incremental cost I C, that is 20.44 plus 0.2284 P g rupees per megawatt hour, right. Now, at 100% rating P g is equal to 50 megawatt, therefore, I C will be rupees 34.64 per megawatt hour, right, and exact cost for C P g 51 if you substitute here in that expression whatever you have got for C P g, that is your rupees 1634 per hour, right. So, this is a simple example we have taken, that how to make the, how to get this, or some ideas you will get, right, regarding that economic operation, right, these some ideas. Next is that general problem formulation. So, slowly we will enter into the detail, right. Now, consider a system you have m number of generators are committed and all the loads PLI given. Actually, you have suppose you have n bus problem, right, in a power network, and out of which suppose you have your all the buses you do not have your generators, you have m number of buses generator, right. So, that means m is equal to, I mean math less than n, say, right. So, you have m generators committed and all the loads PLI given. So, you have your objective will be find PGI and voltage magnitude Vi, right, for I is equal to 1 to m to minimize the total fuel cost. Now, in our here in this thing we will not go to solve that what is will be our Vi, because for that you need detailed load flow and this and your large problem, then only we can manage it, right. That is without computer we cannot do it actually, right. So, whatever this whatever will come as far as the classroom exercise, that way we will do, right. So, the total fuel cost can be given, you have m number of generators, therefore, I is equal to 1 to m Ci Pgi, this is equation say 6, right. Now, question is that your subject to the satisfaction of the power flow equation, that is the load flow equations, right. That means load flow equations that is called equality constant in power system, right. And the following inequality constant, like generator power, you have a minimum maximum limit of generator power, voltage magnitude also you have a minimum and maximum value, and line power flow, right. Line, because every line conductor, every transmission line conductor has its maximum power carrying capability or maximum current carrying capability, that they call thermal limit, right. So, you have to put the bar, right, that means limit has to be put, right. Just whatever you want you cannot do that, that means so many constants are there, right. So, those this is equation 6, right, this is equation 6. So, that means that first constant is that PGI generation must be greater than equal to PGI mean and less than equal to PGI max for I is equal to 1 to m, because you have m number of generators, right. And voltage magnitude Vi must be greater than equal to Vi mean less than equal to Vi max, I is equal to 1 to m again, right. And the power flow, that Pij mod Pij less than equal to say mod Pij max, I mean it has to be less than equal to that. So, this is for all the lines, right. So, many constants are there, right. So, we will take judiciously that how to solve this. So, when you are solving economic load dispatch problem, then you have to see that all the constants also are not violated, right. It has to be within the constant, right, and within the constant only you have to optimize the thing. So, brief explanation on the problem formulation is given below. The power flow or load flow equation must be satisfied, that is true, you have to solve load flow, right. For large problem, even if you take large problem, you have to solve the load flow, without load flow you cannot move, right. So, therefore, they are equality constants in the optimization process, because you are solving load flow. So, it is equality constants, right. So, that is first is load flow. The second one is the lower limit on PGI is due to boiler and or other thermodynamic consideration, right, and the upper limit is set by thermal limits on the turbine generating units, right. So, the voltage constraint will keep the system voltages near the rated or nominal values, right. The voltage should be neither too high nor too low, right, and the objective is to help maintain the consumer's voltage. You have to maintain the voltage, right, such that at the consumer end the voltage should be within the limit, right, I mean within the permissible limit, right. So, that is why voltage constant also must be, you have to be careful, right. And fourth one is constant on transmission line powers relate to stability and thermal limits, that also you have to consider, right, that your line flow, the transmission line your power flow limit, that also you have to consider, right. And these are the several constants, right. And the minimization of cost function Ct subject to equality and inequality constraint is treated by a branch of applied mathematics called nonlinear programming. So, using nonlinear, several different type of nonlinear programming, one can solve this problem, right. But nowadays that soft computing techniques are available, right. Although here I have written something that computationally that this nonlinear programming technique very expensive in the sense that of course, you know, it will computationally it may take more time, but soft computing technique if you apply, that will give you global optimum value. In that case what will happen, it takes more time than nonlinear programming, but question is that this kind of nonlinear programming method, there is a strong possibility that it will stuck to local optima, that means either local minima or local maxima, right. But whereas this thing for soft computing technique actually, right, your generally it gives the your what you call that global optimum value. So, that is why nowadays people are solving this kind of problem using different type of soft computing techniques, right. So, anyway, so we will follow we will not follow here in soft computing technique, that is a different thing, right, but we will see using this your what you call classical optimization method, right. So, but before that, to solve some approximate methods to simplify the problem for, that is why I have written nonlinear programming methods do not easily give the insight into the nature of the optimal solution, and computationally they are very expensive, right. So, I mean it takes time, but soft computing technique though gives your global optimum, but it takes much more time, right. But in some approximation, but your what you call and your there are many comparisons will be there between this classical optimization method and soft computing methods, those are not discussable here, right. But if you send a mail to me, I can tell you that what are those differences, right. Hence, some approximation will be made to simplify the problem formulation, and it gives the physical insight into the problem of economic dispatch, right. So, what we will do, we will first go for a classical economic dispatch neglecting losses, right, because we know the generation is equal to load plus losses, right. So, first we will consider that without power loss, without I mean neglecting power losses, right. So, this is classical economic dispatch neglecting losses, right. Let us assume that which generators are to run to meet a particular load demand are known a priori, right. You know, suppose you have so many generators and you assume that which generators will run, that you know that is known to you, right. So, suppose you have m number of generators. So, Ct will be the total Ct will be I is equal to 1 to m Ci Pgi, this is equation 7, right. Subject to that generation, total generation I is equal to 1 to m Pgi, that means Pg1 plus Pg2 up to Pgm is equal to the PL is equal to total load. Loss is not neglected, loss we will see later, at that time it will become PL plus P loss, that we will see later, right. Is equal to I is equal to 1 to n PLI. In a power system you have n number of buses. So, I is equal to 1 to n, that is sigma PLI, this is equation 8, right. And your this PGI, must be within this limit, that PGI mean and PGI max for I equal to 1 to m, this is equation 8, right. That means equation 8 can be written sigma your y is equal to 1 to m Pgi, the total generation, minus PL, that is total load, PL is equal to sigma I 1 to n PLI, right, that is equal to 0, this is equation 10. Now, also for the time being, do not consider generated power limits given by equation 9, for the time being we will not consider this generation power limit, right, for the time being we will not consider it, right. Therefore, the problem can be solved by the classical method using Lagrange multipliers, right. So, for minimizing or maximizing or in general for optimizing, right. So, a function with equality constant as side conditions, right. So, using the method we replace the cost function Ct by an augmented cost function Ct tilde, that is Lagrangian as. So, Ct tilde we can write, that is augmented cost function is equal to Ct minus lambda in bracket sigma I is equal to 1 to m Pgi minus PL, right. So, that is your this constant, this was your equality constant, this one is your equality constant, right. This one we are bringing into this augmented cost function, that C t tilde is equal to C t minus lambda in bracket I is equal to 1 to sigma p g I minus p l. When solution will converge, sigma p g I will be sigma p l. So, this term will vanish, I mean it will be 0, right. So, at that time C t tilde will be C t, right, but minus lambda multiply, right. Now, that means C t tilde equal to I is equal to 1 to m C i p g I, right, minus, because C t is equal to sigma I is equal to 1 to m C i p minus lambda in bracket I is equal to 1 to m p g I minus p l. This is equation 11, and while lambda is the Lagrangian multiplier. Actually lambda it has become my habit. Actually lambda is this one, this is the lambda, but this has become my habit. So, please forgive me for that, right. So, this is actually lambda is the Lagrange multiplier, right. Next, what you have to do is that minimization can be achieved by the condition d c tilde that d p g I equal to 0, right. This condition you can put, therefore, d c I d p g I minus lambda is equal to 0, right. If you take the derivative of this one, right, with respect, I mean d c t your derivative of this one delta p your p g I, right, then it will be your d c I d p g I, and here also if you take with respect to ith one, then only minus, this is constant and you are taking derivative with respect to ith one, it will be minus lambda, right, into 1. So, that means this is minus lambda is equal to 0. That means this d c I d p g I equal to lambda for I equal to 1 to m. This is equation 13. The d c I d p g I equal to I c I is called incremental cost of the I generator, right. So, I c I, right. That means equation 13 can be written as d c 1 upon d p g 1 is equal to d c 2 upon d p g 2 up to this a mth term d c m upon d p g m is equal to lambda. That means what? That incremental cost for the your what you call optimum operation for all the generating units, they are equal lambda, right. Therefore, optimal loading of generator occurs correspond to the equal incremental cost, they are all equal incremental cost, right, point of all the generators. That is equation 14 is called the coordination equation. This equation is called coordination equation, right, and m number of equation if solved simultaneously, right, with the generation load balance, that is equation 10, right, to give a solution for the Lagrange multiplied lambda and the optimal generation of m generators, right. That means system will operate your optimally whatever cost fuel cost curve you have C 1 C 2, right, but their incremental cost curve, incremental your cost value, that d c 1 d p g 1 d c 2, they all have to be same, right. So, this is the condition when we are not considering the losses, right. So, this is actually how this, and this equation is called coordination equation, one has to solve, right. For example, you have a cost characteristic of two generating units. One is like this C 1 P G 1, this side P G 1, another is C 2 P G 2, this one. So, this is another type of characteristic, this is another type of characteristic, right. Suppose if you increase there, right, for example, this is the slope you call I C 1 for unit 1, this is the slope somewhere I C or is equal to I C 2, right. So, if you suppose some load has changed, right, some load has changed. So, naturally the generator has to increase or decrease, right. Ultimately your for that if you change it, I mean this is 200 megawatt, this is 100 megawatt, right. So, if you try to find, if you just your what you call, if you try to adjust P G 1 and P G 2 for example equally say, right, although in reality optimal will be different, right. So, in that case you will find that changes, that what you call your delta changes here and there because some load has changed, right. You will find the slope I C 1 and slope I C 2 will be different because this cost characteristic is different for a change in your what you call that load. If change the load, generation will change, So, for that way the slope will be different. If it moves from this point to this point it comes, or if it moves from this to this point, you will find from that graph also something has been drawn so that you will find slopes are different, right. So, two generators are different incremental cost ICs, right, but they have to operate at equal ICs, right. So, that means if you look into this, suppose if I have 3 generating units, right, then this is say this side is a lambda and this side is 3, this is IC1 incremental cost curve for this one. Actually whatever we have taken, that quadratic object quadratic cost function Ci, right, Ai plus Bi Pgi plus Di Pgi square. When you take the derivative, right, it will be linear, but if you take cubic it will be not linear, it will become slightly quadratic, right. So, instead of drawing that this linear one, I have made little bit of curvilinear, right. You can make it linear also, no problem, right, but this one what will happen, although they have 3 different ICs, right, your IC1, IC2, IC3, right, 3 different ICs, right, and PG1, PG2, PG3, but they all have to operate at equal lambda, because we saw no dC1 upon dPg1 is equal to dC2 upon dPg2 up to dCm upon dPgm is equal to lambda. So, they all have to operate at equal lambda. So, it said this is the lambda value. So, at this case if you see generation for this one Pg1, this is Pg2, this is Pg3, right, their generation Pg1, Pg2, Pg3 actually completely depends on their cost characteristic, that and the slope also, right, their slope also. So, that is the incremental cost curve and this is Pg megawatt, although it is linear, but once again repeating that this is your little bit curvilinear I have taken, right. So, this is your what you call that some ideas about the incremental cost, right. Next is that algorithm, that how to solve this one, solve this problem. So, in this case the complete algorithm is given below. For example, step 1, you have to choose an initial value of lambda. Later we will see the gradient method how we will go for iterative way, but for this one choose an initial value of lambda, that is IC is equal to IC0, suffix 0 is here, right, that is lambda, that is IC0, right. Step 2, solve for PGI using equation 14, right. So, using that is your this coordination equation, that means this equation, that is your coordination equation, this equation you have to solve, this one, right, this one you have to solve. Then your what you call, then you have to check the absolute value, right, that I is equal to 1 to m PGI minus PL, minus PL, whether it is less than epsilon or not. Epsilon is a small specified value, that you convergence characteristic you put it, because generation has to match load, loss is ignored for this case, right. So, optimal solution if it is reached, the optimal if it is less than epsilon, optimal solution is reached, otherwise you have to go to step 4, right, I mean next step you have to go. So, in that case what will happen, that now you check if sigma I is equal to 1, I mean total generation minus load, if the difference is negative, then incremental cost IC0 you increase it, later iteratively you will see it, but IC is equal to IC0 plus delta IC, that you this thing what you call you increase it, or if it is positive, if the total generation minus load the difference is positive, then IC is equal to IC0 minus delta IC. In this case you increase the generation, in this case you decrease the generation, right, and go to step 2, again from the step 2 you have to repeat. This is possible because PGI is monotonically your increasing function of IC, right. So, that we have seen the previous one, that with the increase on PG that IC that is increasing, right. So, that way these conditions are considered, right. Therefore, this is the thing. So, this is the idea that how to solve it. Later when we will take numericals we will see that, right, at least 7 I think, I cannot recall now, perhaps 8 numericals we will solve for this particular topic, right. Now, suppose for a given PL0, right. So, this is your suppose for a given demand PL0, that means some demand is given PL0, right. So, optimal generations are PGI0 and corresponding cost is CT0. Suppose initially it was total load was PL0, this PL0 is a superscript, right, and similar, and at that time total generation was PGI0, loss is ignored and corresponding cost is CT0, right. Now, assume that load increases to make PL is equal to PL0 plus delta PL. So, load has increased, load has changed by delta PL, right. So, PL is now PL0 plus delta PL, and we have to obtain the new cost CT. We may use two term Taylor series. So, CT is equal to CT0 plus a delta CT, right. CT0 is equal to CT is equal to CT0 plus delta CT, right. That means your CT is equal to, right. If it is so, then CT is equal to your sigma I is equal to 1 to m, that is Ci Pgi 0 plus DCI Ci Pgi, actually Ci is a function of Pgi 0. So, DCI dPgi into delta Pgi, this is equation 15, right, because CT is taken as your what you call CT0 plus delta CT, right. We have to obtain a new, we may use two term in Taylor series. That means, this CT we are actually writing that I is equal to 1 to m Ci Pgi plus DCI Pgi 0 dPgi into delta Pgi, this is equation 15, or CT is equal to I is equal to 1 to m, this term Ci Pgi plus, right, I is equal to 1 to m DCI Pgi, instead of again and again telling function of that, understandable, DCI dPgi into delta Pgi, right. So, this term, this is actually CT0, therefore, CT, then CT is equal to also you know CT0 plus delta CT, because CT is equal to your CT0 plus delta CT, no equation number is given here, CT0 plus delta CT, and here also that means CT we are writing CT0 plus delta CT is equal to CT0, because this term is CT0 plus that sigma I is equal to 1 to m d dPgi into delta Pgi. So, CT0 will be cancelled, therefore, delta CT will be I is equal to 1 to m d dPgi into delta Pgi, this is equation 16, right. That means, delta CT will be this one. Now, we know lambda is equal to your DCI dPgi, this you know that incremental cost lambda, right. Therefore, in this equation you this one you replace it by lambda, right, this equation 16 you replace it by lambda. So, if you do so, then lambda, then delta CT will be equal to lambda I is equal to 1 to m, your sigma I is equal to 1 to m delta Pgi, this is equation 17, right. Now, that as the for a small change in, this is the small total change in some load delta PL, that is basically nothing but summation of all the generation change, that is sigma I is equal to 1 to m delta Pgi, right. So, that means whatever load change, generation has to accommodate that, because generator has to generate that power, loss we have ignored here, right. So, delta PL is equal to this much, that means this one is equal to delta PL, you put it here, therefore, delta CT will be equal to lambda into delta PL, right. That means what? What does it mean? This thus lambda is the constant of proportionality relating to cost rate increase, that is rupees per hour, to increase in system power demand, right. So, basically when there is a that is another significance of lambda, that load has changed, right, but delta CT actually what you call directly proportional to that your total change in load delta PL, and that proportionality constant actually is lambda, right. That is why thus lambda is the constant of proportionality relating the cost rate increase, that is whatever it increase the rupees per hour to increase system power demand, that is in megawatt, that is the your what you call, this is that physical significance of lambda also, right. Thank you.